Good morning, everyone, once again. Welcome to this Water Institute Water Talk at the University of Waterloo. My name is Roy Brouwer. I'm the Executive Director of the Water Institute. I want to start by acknowledging that we're participating today from traditional territories of the First People across the country. Here in the Waterloo region, I acknowledge that I'm on the Haldimand Tract, land that was promised to the Haudenosaunee of the Six Nations of the Grand River. The Haldimand Tract is within the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. I would encourage you to take a moment to recognize the traditional land where you are. And for those interested, the Water Institute is happy to provide you with links to the various land acknowledgements of First Peoples and traditional territories across Canada. Before I introduce today's moderator, just a few housekeeping items. Please add your questions to the Q&A box and not to the chat box, please. You can do that at any time throughout the talk, and my Water Institute colleague, Nancy Goucher, will help the moderator and get to those questions at the end. Use the chat box just for general comments on technical issues. And this webinar will, as always, be recorded and posted afterwards on the Water Institute's YouTube channel. So at this point, I will introduce the moderator for today, Professor Simon Courtenay, the chair of SERS, the School of Environment, Resources and Sustainability. Simon and the speaker know each other already for a while, and I'm happy to hand over the moderation of this session to him. Simon, thank you very much for being the WaterTalk host today. Over to you to introduce the speaker.
Many thanks, Roy. Well, it's a real pleasure to introduce my friend and colleague of many years, Bob Bailey. It's always tempting to include too much information in introductions, particularly about really fascinating people. I'm going to resist that temptation today because that ends up being very distracting. For example, if I told you that Bob's passion outside of work is community theater, and that he has even got his own radio program every second week talking about theater, you'd spend the whole of his talk thinking, can I really see this guy singing in musicals and directing the Sunshine Boys? And that would just be distracting. So I'm not going to do that. I'm just going to stick to Bob's professional bio sketch. After doing his bachelor's and master's at the University of Guelph and a pre-doc at the Institute for Environmental Studies at the University of Toronto, Dr. Bailey completed a PhD on freshwater mussels with Professor Roger Green at Western University in the late 1980s. In case you don't know him, Professor Green literally wrote the book on sampling design and statistical methods for environmental biologists. So it was a huge influence on Bob, and will, I'm sure, show up in this talk, and has been a huge influence on many of us. Dr. Bailey then stayed on at Western as a professor for more than 20 years, where he worked with Trevor Reynoldson and Richard Norris to develop and refine the reference condition approach, the RCA, for bioassessment of freshwater ecosystems. And with colleagues and students, Dr. Bailey has applied the reference condition approach to assessing the effects of human activity on streams in Canada, from placer gold mining in the Yukon to intensive agriculture in southwestern Ontario here, to former coal mining areas in Cape Breton. In 2015, after 5 years as the provost of Cape Breton University, Dr. Bailey moved to Ontario Tech University, where he is now and has held various senior administrative positions. And currently, Dr. Bailey is back to being what he calls a real prof again, focusing on new ways to model biological change in freshwater ecosystems with big data from remote sensing and GIS. He's currently a professor in the Faculty of Science at Ontario Tech University. So it's a real pleasure to welcome Bob to give us his talk today titled, This Year's Model, Crafting Better Predictions to the Reference Condition Approach to Bioassessment of Freshwater Ecosystems. Over to you, Bob.
Thanks very much, Simon. The traditional Zoom greeting, I guess I'll say, can you hear me? And Simon, if you could give me thumbs up when you can see my first slide, that would be wonderful. Okay. And yeah, thank you so much. It's great to be here with you. And just to echo Roy's land acknowledgement, if you haven't checked out nativeland.ca, really, I strongly recommend it. It's a great way to learn about the traditional territory that you're from. I know we're coming from everywhere today. For myself, I acknowledge with humility and thanks my neighbors, the Alderville First Nation, about 10 kilometers east of me, and the Hiawatha First Nation, just across Rice Lake, about 5 kilometers north of me. As I said, great to be with you, even in such unusual circumstances. I recognize the irony of my title slide. This incredible album came out in 1978, believe it or not. And I'm just a few years younger than the great Elvis Costello. But I thought it'd be interesting to talk about how I've totally changed my view of how we analyze data and build models to assess ecosystem change in response to human activity. So that's what I'm going to talk about today. I finished up this little book with Richard Norris and Trevor Reynoldson almost 20 years ago. And on that note, I recommend that all LCRs, late career scientists, late career researchers, reread your old literature. Much that you read will make you roll your eyes or blush, but there are a couple of things in this work that I still like. I go back here. A couple of things in this work that I still like, in spite of the 90s era graphics. The figures on the right, and I think I can get a pointer going here. Hang on one sec. There we are. So the figures on the right really, for me, still show the essence of the reference condition approach to bioassessment. On the top there, you see that the biota in healthy ecosystems varies. That's the vertical height of that box plot. We're assessing whether or not ecosystems exposed to human activity are within or outside of this range of variability. So there's a passing test site, as we call them, within the reference condition range. Here's a failing test site outside of the range with respect to some descriptor of the environment. The other key part of the RCA is in the lower figure, where part of the variability in healthy ecosystems is explained by variation in the environment that they're in. And we assess whether or not ecosystems in a given environment that are exposed to human activity have the biota that we would expect if they were healthy. That's the open dot here. Or they're outside of, or they don't have the biota we'd expect given their environment. That's the closed dot here. So again, on the y-axis, we have some descriptor of the biota. On the x-axis, we've got some descriptor of the environment. And this graphic represents this model, which is showing how the environment can help us predict the biota we see in healthy ecosystems, in these reference ecosystems. The other thing that we did in the little book was, I think, one of the first uses or applications of what we called Simpacks in using the reference condition approach. And Simpacks, I guess initially motivated by Simon Link, he did some great work on what he called the imperator. But Simpacks are important because the only way we can tell when we're doing bioassessments of real ecosystems that have been exposed to human activity, the only way that we can tell if the bioassessment technique is working is if we simulate the degradation of healthy ecosystems. So in this table, which is from the book, we defined what we called a diversity Simpact of the 252 Great Lakes, nearshore Great Lakes reference sites that were part of this data set. So we took each of those reference sites and applied a Simpact, applied a simulated degradation to each of the reference sites. And then we subjected those Simpacted sites to our analytical method to see how well they worked. And what you can see, you just get the basic descriptors of the reference sites in terms of taxon richness, something called MC-DIST, Oz Rivers OE50, and a B-score. So you see that for reference sites, diversity Simpack sites and test sites, sites that were really exposed to human activity in the table. But what I want you to focus on lower down here is how those Simpacted sites did with different RCA analytical approaches in terms of our ability to detect their degradation. And they didn't do very well. So with all three techniques that we use, let me just move this Zoom stuff out of the way here. I can see what I'm showing you. With all three of these approaches to deciding whether a simulated degraded site, a Simpacted site, was degraded or not. In the case of the Ozriba's approach, 91% of them passed. In the case of the BEAST approach, 84% of them passed. And in this MC-DIST approach that we defined in the book, 75% of them passed. So we weren't, generally speaking, we weren't detecting this simulated degradation with our techniques. So that it was really helpful for us to really figure out what was working in terms of the technique and what was not. So flash forward, if I can, about 10 years after that. And in the mid 2010s, around about 2013, we honored our dear friend, our colleague, the late Richard Norris, at a session of the Society for Freshwater Science, where several research groups carried out their approaches to RCA bioassessment on the same three data sets. A common Simpact algorithm, which you see summarized here in this table, was used to create 4 known levels of degradation in each data set. So there was no degradation, there was so-called mild, moderate, and severe degradation. And you can see what was done to, again, simulate this degradation. And then each of the groups got the 3 data sets with the simulated levels of degradation, and they had at them with a wide variety of models or analytical approaches that they used on them, so that we could compare the results of different analytical approaches and how well they did the bioassessment on these data sets. So what I want to do today is take a closer look at the Great Lakes and Yukon RCA programs, how they did in this sort of head-to-head competition in terms of different analytical approaches, and really explain how those results and the approach that was used here got me rethinking my approach to modeling in RCA and ecosystem modeling in general. So I'll start with the Nearshore Great Lakes RCA program, and the data that was used, that was distributed among these groups of researchers, summarized in the blue box at the bottom of this table. So this is 10 years worth of this long-standing Great Lakes, Nearshore Great Lakes sampling, done with box core, mini box core, or Ponar. And the basics of it, there was 124 so-called training sites. Those were the sites, reference sites used to build this model which related the environment to the biota. There were 40 so-called validation sites. These are reference sites that were not used to build the model. And as you can see from the table, there was, in this data set, there was a median of 7 family. It was family level identification was used. So a median of 7 families found at reference sites. It varied from a minimum of 3 to a maximum of 24. Abundance, median abundance in those reference sites was just shy of 9,000 individuals. So the modeling exercise, and this is I guess where my head started to turn, as I'll talk about in a few minutes. The modeling for the Great Lakes project, what I call the no-cause RCA model, basically took the list of candidate predictors that you see, and this is the case for all of the groups, all the different research groups applying their approach to the Great Lakes data set. So as you can see, I hope you can see on the table at the left, there's everything from lat and long, chemistry of the overlying water, including depth, alkalinity, DO, pH, and so on. Nutrient concentrations, that's in the water, and then sediment quality. So sediment particle size and element concentrations. So a whole bunch of predictors. And as I said, a variety of methods were used to take that laundry list, or what some people would call kitchen sink of predictors, and build a model that related some subset of those predictors to the biota found at reference sites, which led to that second step of the model that I talked about at the beginning, where we could judge whether or not we were seeing what we would expect for a healthy reference community at a site given its environment. So how did the Great Lakes data set do with the different researchers? Well, here you see in the table 6 at the bottom, and I've got in the blue box at the right here, the results from the various research analytical approaches from the research groups with the Great Lakes data set. So let me just orient you a little bit here. The first column, which is labeled PDO, is the proportion of sites that failed of the undegraded sites. So these are reference sites that failed according to the analytical method used. And so this is, of course, type 1 error. This is rejecting the null when it's true. So concluding that a reference site is out of reference when it's really in reference. So it's a measure of type 1 error. And if you look down that column, you can see that the type 1 error rates, especially for analytical approaches that are actually commonly used in big programs, are pretty high. You know, what this is saying, for example, with Trevor's analytical approach here is that 48% of the sites known to be in reference condition were failed by his approach. And this isn't a knock at Trevor, by the way, and his group. I'm just trying to, again, acquaint you with how the evaluation was done of different assessment methods. So we've got that to look at. And as you can see, there's some variability in that type 1 error rate, depending on how the analytical approach used. Bruce Chessman's approach down here, only 7% of the known reference sites failed with Bruce's analytical approach. So if we look at the PD1 to PD3, these are the 3 levels of degradation, greater degradation. And so the proportion of them failing is really a measure of the power of the analytical method to detect a deviation, a degradation from reference condition, an unhealthy ecosystem. And you can see that with the methods we were talking about before, the Trevor's method, for example, okay, 48% of the mildly degraded sites failed, only 38% of the moderately, and 43%. And of course, the devil's in the details, because that's not much different than the method was attributing or concluding was an unhealthy ecosystem than the reference sites themselves. So that was our measure of how the methods, different methods worked relative to the nature of the data sets. What I concluded in looking at that and re-looking at that, and I guess rethinking about that, was the challenges of what I call the no-cause RCA model is, first of all, the data are driving the model. So the various techniques that were employed all had an approach which picked out predictors or combinations of predictors from the list you see at left there and formed the model based on those data. The candidate predictors, in several cases that you can see here, and I'll leave it to my limnological colleagues to kind of piece this through, or we could talk about it later, are potentially affected by the stressors. So this list of potential predictors are really supposed to be describing the natural environment. And in many cases, variables on that list are going to be affected by the stressors we're worrying about that are going to affect those communities in nearshore Great Lakes environments. Also, the so-called kitchen sink approach to building a model to use the environment to explain variation in the reference biota is very sensitive to confounding and overfitting, which we'll talk about in a few minutes. The other challenge here is that Simpact algorithm that I mentioned a few minutes ago, you know, the D0 to D3 levels of degradation that were simulated and applied to the data set is very naive. So, and it was the same as we'll talk about with the Yukon data in a minute. It was the same approach used with all three of the data sets that were employed in this sort of head-to-head competition. So what are my recommendations? First of all, to build and test a causal RCA model using environmental descriptors that are unaffected by stressors. And I just a couple of examples there, neither of which are on this list, are the adjacent terrestrial ecoregion of the site and fetch. You know, what's the site's orientation relative to wind direction? So how much turbulence, it's a relatively complicated calculation, but possible. How much turbulence is present at that site, depending on where it is, what its orientation is, and so on. Those are, to me, two obvious, among others, two obvious potential predictors that are unaffected by the potential stressors involved in the system. The other thing that I think would be worthwhile to do to get a more credible set of Simpacts to evaluate the model is to build and test a causal Simpact model that uses relationships between, uses known relationships between stressors, for example, sediment quality, and the biota. So that actually builds something that then generates simulated, degraded communities. It's sometimes called counterfactual, pushing predicted relationships between stressors and biota to really create much more realistic Simpact models. Because one of the defenses in various of the analytical models not doing so well in this context was that the Simpacts didn't really reflect what really happens to nearshore Great Lakes sites when they're affected by stressors, when the biota change. So basically, my two recommendations boil down to build a better causal RCA model, and I'll show a little example of that in the third part of the talk, and to build a more realistic causal Simpact model to really do a good or a better job, I think, of evaluating and improving assessment approaches. So let me spend a few minutes looking at the Yukon River Basin stream program, which was a second data set in this sort of head-to-head competition. I guess a shout out there to my brother John and Simon Linke, who are there electrofishing in one of the Yukon streams that we sampled 15 or 16 years ago. So this data set, in this comparative study, we used a couple of years of the sampling. This is again in wadable streams in the Yukon River Basin. Traveling kicknet approach. There was, in this case, 118 training sites or model building sites, and 40 validation or model testing sites. And I just want you to see if yeah, I've still got my pointer. So the median site richness in this case was 10 taxa, again, family level taxonomy, varied from 1 to 22 taxa. So I guess if we're comparing the Great Lakes, the nearshore Great Lakes, yeah, there seem to be a few more, generally a few more taxa at a site, about the same variability. But what I want you to see is the last column, which is abundance, median abundance, 263 individuals, and as compared to almost 9,000 in the Great Lakes sites. So different, I was gonna say different kettle of fish, different bottle of inverts in the Yukon site than the Great Lakes site. And I guess something to point out as we go by here, keep in mind, again, the same algorithm in terms of generating those Simpacts was used for this obviously very different system than in the Great Lakes site. So in the case of, I've got on the left here the laundry list of candidate predictors that were used in the case of the Yukon program. And you can see that, again, they vary from the geographic. In this case, we've got lat long again, but also catchment area and descriptors of the catchment itself for the stream sites. We've got so-called GIS parameters, including land cover in the upstream catchment, bedrock geology. We've got some climate predictors. We've got local predictors in terms of the stream channel and water. But suffice to say, again, you know, a little bit of dramatic foreshadowing, I guess, that we have this kitchen sink approach where, you know, let's put stuff in, let's try to avoid predictors that are affected by stressors, but let's throw everything in and see where it lands, to be somewhat cynical. And I'm being cynical towards myself, by the way, because I certainly helped develop a lot of this stuff. So here's the results for the Yukon data set, and you're all oriented now. So I know that you know this column that's PDO is the proportion of the actual reference sites, non-degraded sites that failed. So type 1 error here. And as you go down the list, you can see again the 3 techniques that are commonly applied in big programs had quite a high type 1 error rate. That means they're considering unhealthy, a fair number of sites that are okay. And I think I have some of my grad stats class here, and as they know only too well, and I think a lot of folks listening will know, what we really have to think of is, oh geez, that's too high, but we really have to think about the relative importance of that type 1 error rate. You know, what are the consequences of rejecting or failing a site that's actually okay versus concluding a site's okay when it actually should fail? So that's nothing to do with stats. It's really a decision which looks at the environmental and other consequences of those mistakes. But anyway, fairly high type 1 error rates with widely applied program methods, a little bit better with other novel techniques that were developed by the groups that you see there. When we get into power, that is, what was the probability that a site known to be degraded to a certain degree, things are a little bit better on those widely used methods side. As we get to extremely degraded sites, then most of them are failing, which is good. So our method seems to be, these methods seem to be more effective at detecting that extreme degradation. So conclusions from the Yukon Basin study won't surprise you now. Very similar to my conclusions about the Great Lakes study. First of all, the challenges with the no-cause RCA model again, the data are driving the model. And I'll really put on the table what I mean by that in just a couple of minutes. I have a problem with that. So the data driving the model, the candidate predictors, there's several there, and we could have a great chat over a beer if that was possible. It will be possible someday, about which of the predictors that you see in that laundry list over there are potentially affected by the relevant stressors in this case. Relevant stressors in this case include largely placer gold mining at various scales in affecting Yukon streams. There's also, again, the obvious challenge with the kitchen sink approach to just having all of these as candidate predictors, and that's sensitive to confounding among them and overfitting. And of course, we still have that same naive Simpack model that was used here. So my recommendations are the same. Build and test a causal RCA model using environmental descriptors unaffected by stressors. In this case, there's been a lot of great work done in the Yukon in particular, obviously more widely on ecoregion. That could be a great predictor of what you're going to see in the stream if it was looked at. And catchment area, which is already in their laundry list, is another great candidate predictor, unaffected by stressors. Second, again, just as in the Great Lakes context, to build and test a causal Simpack model using relationships between stressors, in this case, for example, suspended sediment and the biota. So here I am, having made a lot of criticized these models a lot, and I want to talk about with an example. I'm just glancing at my watch here. Okay, I want to talk about with a little example how I am trying to I guess make some progress in building causal models. And I just want to pause here and really recommend Richard McElraith. This is a figure from Richard and some of the stuff he's done. He's got this great book called Statistical Rethinking, available on Amazon, 2nd edition. But he also has, as a companion to that, incredible YouTube short courses. I just assigned one, and I hope all you grad stats class have seen that first lecture that I assigned. Richard is brilliant, much more brilliant than I, in talking about building models that are based on cause, a causal concept of, in our case, how stressors are causing degradation of ecosystems, or how natural environment descriptors cause the biota that we see at reference sites. So I highly recommend his work. The challenge of cause, and what's sort of the cartoon here, I should mention, of course, that quote in the bottom, which I used to proudly make at every time I talked about RCA, is I don't care about cause or mechanism. I just want to predict. I want to use the the laundry list that we've seen to predict what I'm going to see in a reference, or what I should see in a reference site in terms of biota based on its natural environment. So when you start worrying about cause, that is, what variables in the environment actually cause changes in the biota, there's several issues you have to deal with. And just the main culprits here, the fork, the pipe, the collider, and the descendant, I just want to talk about briefly before I quickly show you my foray into causal modeling. So first of all, the fork. And I should say, by the way, we've all dealt with all of these, and all of these are permeating the models that I've shown you with the candidate predictors I showed you regarding both the Great Lakes and the Yukon site. So the fork is when there's a variable that's affecting two other variables, and that causes a correlation between the two of them, even if they're not causally related themselves. So the example I've given, again, which we can debate sometime, is increased fetch will cause a change in both phytoplankton and benthic invertebrates in those nearshore Great Lakes sites. So that can cause a correlation between the phytoplankton and benthic inverts that's not really a functionally caused relationship. The pipe is, for example, when you look at a subset of sites, so if I only look at failing sites that are out of reference, that could actually eliminate a relationship between a level of a stressor like suspended sediments in my Yukon sites and benthic inverts. The collider is when a variable is affected by two other variables. So phytoplankton, for example, affected by both water nutrients and benthic invertebrates, which creates a relationship between X and Y at any given level of Z. So that can cause problems when we're trying to build models when you have colliders involved. Descendants sort of like the pipe, but you've measured some kind of proxy, for example, chlorophyll, rather than the causal intermediate itself, like phytoplankton. So you'll be happy to know, I'm not going to go into detail about how to deal with these. I think awareness of them, their potential, is necessary, and McElroy's got great notions of how to tease those out of your model so that you can build a more powerful causal model. So the other part of what I'm trying to do is do what I call taking responsibility back from the data. And that's, I've summarized 40 years of my stats use, advice, and teaching in this one slide here, where, of course, p-values that we've all dealt with endlessly. They're the probability you got the data you did if the null was true. Type 1 error is the chance, if the null is true, the chance of rejecting the null. Type 2 error is if the null is not true, your chance of thinking it is. And we sample the population. This is the paradigm, obviously, of the frequentist, so-called frequentist approach. Sample the population, but you never know the truth. And this is what we've ridden on forever. And one of my favorite slides as a stats prof is this, because I have this sound effect from my good friend Jack, which I hope you can hear. I guess you can't.
You can't handle the truth.
Right. So I have become, as I've told a few people, I have become a Bayesian. And it took me literally years to kind of wrap my head and really appreciate this approach. And as I think a lot of frequentists, I got hung up on priors, hung up on a lot of it. To me, this is my simple explanation, and experienced Bayesians out there can please just reflect, have another sip of your coffee. You don't have to listen to this. But basically, the Bayesian approach differs 180 degrees from the frequentist. And you start with some notion of what the probability is of a multitude of hypotheses, for what a mean is, for what a slope is, whatever. That's your priors, my notion. And I'll show you with a simple example in a sec. Then the so-called posterior distribution is just your notion of what the probability of those hypotheses are, educated by a data set. And then subsequent to that, your refined notion can be what's the probability of those different hypotheses educated by yet another data set. So that to me, that's my cartoon of the difference in approach. So what I want to show you really quickly, I just looked at my watch and it told me the number of steps I've taken today. Don't know why, but I want to show you really quickly with really simple models how I'm trying to apply that, and how Lee Graffentine and I, for example, are going to try to work that into the looking at the Great Lakes data set, or taking a fresh look at the Great Lakes data set. So I'm really taking cause and Bayes, and I'm totally accepting, admitting, realizing there's been lots of great work done with cause, I mean, grad student at Ontario Tech, Tyler Harrow-Lyle, published a great paper last year with structural equation modeling, looking at cause. My colleague Angus Webb, one of the approaches used in the comparison I was talking about, Angus used a Bayesian approach to that comparison. I'm trying to schmuck the two together in a new approach. So let me just show you a couple of quick examples so we have time for any questions. So this is a Landsat image. Sorry, I gotta make sure I watch my script here. this is a Landsat image of in the Trent Severn Lakes area of southeastern Ontario. And this is a Landsat image, the same Landsat image as well, but it's near infrared Landsat image. So it's the near infrared that's being reflected back up to the satellite. And I hope you can see there's some variability. The brightness of the red, by the way, I'm red-green colorblind, but the brightness of the red reflects how much near infrared is coming back to the satellite. And you can see some variability, I think, within the lakes there. So I'm exploiting that because, as many of you know, plants use light in different parts of the spectrum differently. So, and a lot of near infrared and infrared gets reflected back from photosynthesizers, and a lot of that gets received by the satellite. That's the 5-second version of how I'm trying to exploit satellite data to measure and build a model to explain annual variation in macrophyte abundance in Trent Severn Lakes. So here's a picture, a Landsat image as well, from Lower Buckhorn Lake. And this has been pixelated. So Landsat images are 30 by 30 meter pixels. And so what I've done here is created, there's, I think, about 14,000 pixels in Lower Buckhorn Lake. And each of those pixels has a brightness relative to the amount of near infrared that's coming back to the satellite. So what I'm building my model for, and sort of showing you this new approach, is how macrophyte abundance, as measured by that reflectance of near infrared, varies within and among times in Lower Buckhorn Lake and eventually the Trent Severn Lakes. So this is August 2020, and I'm going to show you my very first DAG, my directed acyclic graph. This is how you sort of put to paper what your causal model is for what's going on in your system. And my very first DAG and Bayesian causal model, you see it right there. So it's just the macrophytes at time t1. That's my model. And there in the top left is the specifications of that model. Notice there's no data here yet. So what I'm saying is I'm proposing my priors is that the macrophytes in a pixel at time 1 are normally distributed with a mean of mu and standard deviation of sigma. Mu is normally distributed with mean of 25, standard deviation of 5. Sigma is uniformly distributed from 0 to 50. So those are my priors. That's what I'm proposing. And then I'm using the data that I have. I've got those 14,000 pixels here to educate that model. And what I have at the end is the best estimate or the likely range of values for that average reflectance, the amount, the macrophyte abundance in the pixel. Well, that's great, but let's get real there. I want to be able to predict future macrophyte abundance from past macrophyte abundance. So I've got a simple example here of 2 years, August 2018 and August 2020. You can see some variation between those. There's the DAG related to that. It's just macrophytes at time 0 cause macrophytes at time 1, which would then cause macrophytes at time 2. That's my causal model. And here's me proposing that model, that causal model, and then educating it with the data that I have from 23rd of August 2018 and 20th of August 2020. So notice I'm not saying, let me measure the relationship and fit the model. I'm building or proposing the model, including priors, and then educating it with the data. There's the result where the most likely range of the slope value of relating macrophytes in 2018 to 2020 is about 1. And there, for those of you who, like me, approach this old style building a model, there's a scatter plot where you've got the macrophyte, across these 14,000 pixels, macrophytes in time 1 versus macrophytes in time 0. So it looks like macrophytes at time 0 can really do a good job of predicting macrophytes at time 1. But my next DAG shows you that there's so much more going on. There's so much more that's causing that relationship. Up here in my DAG, we've got air temperature over the previous year. We've got precipitation over the previous year. We've got management. We're talking about a semi-managed system of locks and water levels. That's leading to water levels over the previous year. All of that is potentially affecting the macrophytes that we see at time 1. Nutrients at time 1 are affecting macrophytes. And then looking at among the pixels within a lake, fetch, water depth, relative water depth, depending on the water level, turbulence at the point. All of those, in addition to macrophytes at time 0, are going to affect the macrophytes we see. So I have work to do, obviously, in putting that data together and then fitting that model. So that's my story. lots of work to do, but really it's benefited so much from conversations with colleagues, not just over the last year or two, but over the last decade or two. I really appreciate you coming, and I look forward to if anybody has any questions, comments. If you have things that you don't want to embarrass me with by, critical comments, there's my email on the bottom, so please get in touch and gently straighten me out. But thanks very much for listening. Oh, back over to you, Simon, I think.
Excellent. That's wonderful, Bob. Thanks so much. So again, just to remind people, if you have questions, please use the Q&A box in Zoom, and Nancy will read out your questions. Just while people are thinking about questions, we do have a few minutes for that. Just a softball for you, Bob, to get started. In your slide talking about Simpacks, it made me think back to our discussion years ago about multi-metric approaches versus multivariate approaches, and wondering, the RCA approach it requires a lot of data, right? Not just a lot of endpoints, but also a lot of sites, and so. Does that is the fact that it's so data hungry restrict its use for many of the questions that we would want to ask about whether a stream is in what we would call a reference state, or whether it is unimpacted by things?
Yeah, I think, and I should have said the whole multivariate, multimetric thing, I consider kind of a different category of discussion, but I think what you're saying, Simon, I don't know. I've always felt that if we're trying to judge whether or not a place is okay, we really need to get a full appreciation of the variability of okay. We can't walk into a place. One of the first things that I think the RivPax folks, the early proponents of RCA really pushed, and I strongly agree with, is that there's no one definition to what's a healthy ecosystem. And I think we need the data. We need to understand what that variability in good is in order to judge whether or not this specific ecosystem is okay. So if you see on my slide that you can see right now, you see Chris, my wife, and a paddleboard back there in that little bay behind there. And judging whether or not, you know, if we sampled it, there's lots of turtles, other things, macrophytes and so on that live there. Judging whether or not that's doing okay, or is it affected by, you know, my manicured lawn there or whatever, we can only really judge that if we understand what a sort of side wetland looks like in situations where there are not many situations where there are not, you know, adjacent cottage and stuff. So I think in all cases, we're kind of stuck with that data need, if I can put it that way.
That's fair. Thanks, Bob. Nancy, can I throw it over to you? I see we have a couple of questions.
Absolutely. People are very curious about the Bayesian modeling. So one question that came in from Dr. Roy Brower actually is that Bayesian approaches are non-conventional ways of addressing uncertainties. They nevertheless require a quantification of uncertainties. So is this really helping us move forward?
Yeah, I think so, Roy. I mean, and again, I commend Richard's talks, but for me, and I've always tried to be maybe more even-handed, as I think my students would verify. You know, our typical hypothesis testing paradigm, even-handed in the sense of either accepting the null, which I know is, that terminology makes some of old stats profs itchy, but you know, that those two alternatives, is it the null or is it the alternative? That's kind of the dichotomy that we face, I think, a lot of the times in the frequentist world. The Bayesian world, in my understanding, is just, it's quantifying that uncertainty, or to put it kind of the other way around, the likelihood of a whole plethora of hypotheses. You know, this combination of the slope and the intercept, for example. And the way it works is, okay, you got this infinite number of possibilities for the combination of slope and intercept. Which ones do your data tell us are more or less likely? But it's looking among those infinite numbers of possibilities, as opposed to just saying, is the slope 0 or is it not 0? So I'm not philosophical about it as much as I want to get the most possible. I want to use that data to educate me as much as possible. I think the uncertainty is still there for sure.
And just to build on that, because Kelly McKintrick was also asking about this, and you may have answered part of this, but I'd like to give you an opportunity to comment further if you'd like. So Kelly says that he's been trying to understand this a little bit more, and maybe he does a little bit now with your presentation. In your initial results, are you in a different place yet than you would have been with your old approach? Or is it about trying to get further than you did in the past?
Yeah, thanks. And any day that I can say that I explained something to Kelly is a great day in my world. But yeah, Kelly, I joke with my students, I'm never going to test an hypothesis in a paper again. And of course, they joke back that I'm never going to publish a paper again. But I'm not so naive. And I think how I talk to them about it is actually a good model of how we have to think. I'm not so naive as to think, I try to give them a good understanding of the frequentist world, because we need that now. We're not going to change overnight to rejecting the frequency world, in spite of the fact that I think a couple of journals are trying to do that. But yeah, honestly, my world has totally changed. And I was, as Simon was saying, I was brought up at Roger Green's knee, and Roger's all about, I hope he's not on this, I hope he's not at this talk, we would have heard from him by now. But I really think it's about learning more. First of all, going into what we're doing with a greater, putting more of our science into comparisons, as opposed to people like me building regressions or multiple regressions or discriminant analyses. They don't really understand the system, but let's throw a bunch of predictors in and we'll get a good result, a good prediction. I think really challenging myself to know the system and then seeing, once I've done that, to see whether or not the data support that as I subject my model to the data, as opposed to the other way around. So yeah, it's really changed me, and Kelly, love to talk to you in the future about it. We can sit around and figure out how it changes in detail the worlds that we have to work in.
Great, thank you, Bob. And we're a little short on time, so I apologize for those whose questions we did not get to, but I did want to be able to ask, for those who are new to this modeling approach, would you recommend a few resources so that people can dip their toes in?
Yeah, for sure. And what I'll do, Nancy, is send along that explicit reference. Again, I read a ton of stuff. I've been, more or less on sabbatical, or at least away from my campus for the last couple of years. And I decided at some point, as I reflected on this, to take a deep dive. And I'll send the specifics of Richard's stuff, because I looked at a bunch of stuff, and he is so great, and he has a sort of a cult following. I contacted him. I felt like a fanboy or whatever, but I think that's the key for folks. So I'll make sure that specific reference, along with, he's got like full courses on YouTube, great lectures. So I'll pass that along.
Great, thank you.
Okay, terrific. Well, I'm sorry that we're out of time, but I do want to thank you, Bob, for a fantastic and thought-provoking talk. I suspect your ideas will influence the way that many of us think about how we detect environmental change going forward. So thank you to you, Bob, and thank you also to all of you for coming out this morning for this talk. And in closing, the Water Institute has put together a fantastic World Water Day program for March 22nd. So please visit the Water Institute website for details and to register. And with that, thank you, and have a wonderful Thursday. Bye-bye.